In this video, we will talk about permutations and combinations. Something that is important to keep in mind is that when we talk about a permutation, then the order matters. And while if we talk about a combination, we don't care about the order. This is a key part differentiating permutation and combination. Then let me start defining what is a permutation. Let's suppose that we have n objects. Then we say that a permutation is an ordered arrangement of these n objects. Let's suppose that we have, for example, 4 objects, A, B, C, and D. Then an example of a permutation would be like A, B, C, D, or C, D, A, B, or A, B, D, C. These are just examples. And let's start with the problem of counting how many permutations are possible. We can do that using the basic counting principle. And then we can divide this process of selecting all the permutation into 4 stages. In general, we just be using n stages. Let's say here, let's do a tree, and this is the stage number 1. For the stage number 1, we select the first letter, and we have 4 possibilities to do that, right? Then there are 4 possibilities, but we notice that once we have selected the first letter, then we only have 3 possibilities because we want the letters to be different. Then here we have A, B, C, D. Here the possibilities are, this is A, here we will get AB, AC, AD, and so on. But once we have selected 2, then the next stage is to select the third letter. And then since we have selected 2, then we only have 2 possibilities. And here we have 2. Then in this case, N1 is 4, N2 is 3, N3 is 2, and once we have selected the first 3 stages, we only have 1 possibility for N4 equal 1. That means that the number of possibilities, the number of permutations in this particular example, using the basic counting principle, is going to be 4 times 3 times 2 times 1, which is just 4 factorial. In general, the formula is going to be equal to n factorial, which is n times n minus 1 times 2 times 1. Then this is the number of permutations with n objects. There is another situation, and that is the permutation of n objects taken r at a time. What is this? Let's suppose that we have a group of people. Let's say we have Alex, Tati, Maya, and Oscar, and Ramin. We have 1, 2, 3, 4, 5 people. And let's suppose that this group of people decided to do a race, and we're going to count the first, second, and third place. And then we are going to see what are the possibilities of these positions. Then notice that, as I mentioned before, in this case, order matters because we are going to make a difference in who gets first, second, and third. Then order matters. And essentially, we are selecting the first 3, right? We are taking 3 at a time. Then in this particular example, N is 5, and R is 3. And this is a possibility for Alex. Let's say Alex, Maya, Ramin, right? And I think I can use just the first letters, A, T, M, O, and R. Then I will write this as just A, M, R. This is a choice of 3 elements taken from 5 objects, right? And the order matters. Notice that this one means that Alex got first, Maya got second, and Ramin got third. But if I say R, M, A, that means that Ramin got first, Maya got second, and Alex got third. Then the order matters. That's the reason it's called a permutation. And let's see how many of these can we have. Again, this is a consequence of the basic counting principle. Basic counting principle. And then we can explain this process, this experiment, using stages. And then let's say stage 1. We are going to select who got first. What are the possibilities? In this case, we have 5 possibilities. 1, 2, 3, 4, 5. Alex, Tati, Maya, Oscar, and Ramin. But then for the second stage, this is stage 1. For the second stage, we pick who got second. And then if Alex got first, then we only have 4 possibilities. And if Tatiana got first, we only have 4 possibilities. And here we got only 4 possibilities. And here we got only 4 possibilities. And here we got only 4 possibilities. But once we have selected who got first and second, we only have 3 possibilities. And here we have 3 possibilities. And here we have 3 possibilities. And so on. That means that in this case, using the basic counting principle, at the beginning, N1 is 5 for this particular example. N2 is 4. And N3 is 3. Notice that this 3 would be 5 minus 3 plus 1. Right? Then, in this particular example, if we wonder how many possibilities are for this first, second, and third of these 5 people doing a race, then we have that the number of possibilities is 5 times 4 times 3, which is 60. We have 60 different type of results. What is going to happen in general? If we have n, and we are going to select r at a time, then n1, in general, we will have that n1 is n, n2 is n minus 1, and nr, the last one, would be n minus r plus 1. Then we will end up with the number of possibilities is n times n minus 1 times n minus r plus 1. Okay, then this is the number of permutations of n objects taking r at a time. I think it would be a good idea to write the formula here before I erase it. Then the number of permutation of n objects taking r at a time is just n times n minus 1 times n minus r plus 1. And notice that I can write this in this form. N times n minus 1 times n minus r plus 1 times n minus r times n minus r minus 1 times 1 over n minus r times n minus r minus 1 times 1. Note that this is just essentially 1. That's the reason this is equal to this, and this is the number of permutations. The good thing about this way of writing it is that I can just express this as the numerator is the numbers 1 times 2 times 3, so on until n, and that's n factorial. And the denominator is n minus r factorial. Then the number of permutation of n objects taken r at a time is n times n minus 1 times n minus r plus 1, and that's equal to n factorial over n minus r factorial. Let's continue with an example that shows the difference between permutation of n objects taking r at a time and combination of n objects taking r at a time. Let's suppose that we have the set A equal to A, B, C. In this case, n is equal to 3, and let's suppose that r is equal to 2. And let's do the permutation of 3 objects taken 2 at a time. Then, in this case, we can explicitly see the example. We have AB is one possibility, and BA is another possibility. Remember that for permutations, the order matters. What else do we have? We have AC and CA, and we have BC and CB. But if we are going to talk about combinations of 3 objects taken, then we will have the sets AB, this is one possibility, AC, and we have BC. Then for the number of permutations, we have 6, right? And this agrees with this formula, which is 3 factorial over 3 minus 2 factorial, which is just 6. And for the number of combinations, we have 3. Let's see the reason why this relation 6 and 3. In general, let's suppose that we have m objects, 1 m objects. And we want to count the number of combinations. Then let's suppose that instead of working with the number of combinations, we do the number of permutations. Let's suppose that here are the permutations, and here are the combinations. This is the number that we want to count. Combination of m objects taking r at a time, and here are the permutations of m objects taking r at a time. Then we have this situation. We know how to count this. The number of elements here in this group is n factorial over n minus r factorial. But we don't know how to count this. But we know that there is a relation for each element here. For each combination, we have a group of permutations. We have a group of permutations that goes to the same combination. What I mean by this, for example, for this combination, we have these 2 permutations that essentially uses the same number of elements. For this one, we have these 2. And that number is always the same. And then we have, actually it's not always the same, but it has the same amount of elements. Let's see how many elements do we have. Remember that each one of these groups is just a set with r elements. While here, this one is a set of words. that uses those are elements. Then how many words, different words, can we get with R different elements? The number is just the permutation of those elements, and therefore there are R factorial. And for that reason, we can see clearly that this number that we don't know is exactly the same number but divided by R factorial, because for each one of these elements, there are R factorial elements here that goes there. Then the number of combinations is going to be N factorial over N minus R factorial times R factorial. Let's have this picture with this example. As we said before, for every combination, which is just a group of elements, the order doesn't matter, there are some permutations. For permutations, the order matter, that goes to the same element. And essentially, those permutations that goes to that element are just the permutations of these two elements, which are, in this particular case, there are 2 factorial. And for that that's the reason of this formula in general. Something that is important is that this number is denoted like this, and you call it N choose R. Some particular examples are that N0 is N factorial over N factorial over 0 factorial. And remember that 0 factorial by definition is 1. Then N0 is just 1. Let's do an easy example that uses combinations. Let's suppose that we have 5 people. Person number 1, person number 2, person number 3, person number 4, person number 5. And we want to do a committee with 3 people. How many committees with 3 people can be taken from this? And that's exactly the situation. In this case, N is equal 5, R is equal 3, and then the answer would be 5, 3, which is 5 factorial over 5 minus 3 is 2 factorial times 3 factorial. And therefore, this is 1 times 2 times 3 times 4 times 5 over 2 factorial, 1 times 2 times 3 factorial, 1 times 2 times 3. These 2 cancel out, 3 cancel out, and we have 20 divided by 2. The number is 10 people. Now let's continue explaining this notion of permutation of N objects, where N1 are alike, N2 are alike, and so on. An example that shows something like this is this problem. Let's suppose that we have the word pepper, and we want to see how many arrangements can we do with these letters. Let's see, let me write that down. Okay, to do this problem, we are going to do a different problem. We're going to do something similar to what we did to find out the number of combination of N objects taking R at a time using this. But now we're going to use the fact that the number of permutations of M objects is N factorial. Notice that when you talk about permutation of M objects, then you are just saying how can you just how many arrangements of those M objects, the whole N. But here the situation is a little different. We have N, but we are taking R. But then we're going to compare these two. To make that comparison, we're going to make the letters different. Let's suppose that the letter P's, these P's are different, and the E's are different. Then we have this situation. P2, P3, E2, and R. Then here we have the set of permutations. And here we have the set that we don't know, the set of permutations. In this case, it will be permutations. In this case, there are three objects that are alike. The 3P and 2 are alike. And we can see that there are a lot more of permutation of this than this. But then let's suppose that here we have these elements here. And we know that there are some elements, permutation of this that goes into there. For example, here we have the starting word pepper. And here we have P1, E1, P2, P3, E2, and R. In this same group, we have P1, E1, P3, P2, E2, and R. And in the same group, we have P1, E2, P2, P3, E1, and R. Then we have a bunch of words with the property that if we forget to differentiate the P1, P2, P3, and we just make it a P, and we forgot, and we just disregard the E1 and E2, and when we just make it an E, then we get this answer here for this possible arrangement. Let's try to see some examples for these arrangements. Let's suppose that we have E, P, 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 E, R. This is another possibility. This is another arrangement with the same 5 letters. But here in this group, we will have the permutation E1, P1, P2, P3, E2, R, and we will have the permutation E2, P2, P3, P1, E1, and R, and we will have a bunch of these. But then essentially, to get to know this number, we need to just know how big are these groups. Remember that since we're assuming that all of these letters are different, then we have permutations. Then in this case, we have 1, 2, 3, 4, 5, 6 objects that are different. Then the answer here for the permutations is 6 factorial. For this particular example, is 6 factorial. And we just need to know the length of this group, because this number here is going to be 6 factorial over the length of this group. If this small group is K, then there are K times more elements here than there. But then to find out the length of these groups, we just need to find out the number of permutations of 3 objects. Then we have 3 factorial. Here we are using the basic counting principle. First, we can count stage number 1, number of ways that we can permute the p's, 3 factorial. Number of ways that we can permute the e's, then in this case 2 factorial. Then each group will have 3 factorial times 2 factorial, and for that reason the answer to this question would be 6 factorial over 3 factorial times 2 factorial, which is just 1 times 2 times 3 times 4 times 5 times 6 over 3 factorial, 1 times 2 times 3 times 2 factorial, 1 times 2. This cancel out, and we have 3 times 20 is 60 elements. In general, we have that the number of permutation of M objects is n factorial, and the answer to this question, how many arrangements can we do with M objects, then the answer would be n factorial. Let me write it with red. N factorial over n1 factorial times mr factorial. In this case, as I said before, in this case, n1 is 3, and n2 is 2, and n is 6.